Okay, so I'm sharing this PowerPoint slides in the Zoom session. I hope is uploaded or it's loaded in your desktop as well or in your screen as well, right?
It is.
Okay, so today what we will be focusing on is go through some of the details or some of the concepts that we already have done or we have studied during the lab sessions about the design process or design objectives. Just give me a second. Is this on? Yeah, this is on Beachboard. Yep. So we are going to see some of the processes or some of the concepts that we actually uh, practiced and we actually see in the during the lab sessions, and then we will basically wrap up our discussion with some of the analysis steps about how to use mode circle for design calculations. So we will first see the design process and what are the steps that are required. So just for uh, just for making sure that everybody's on the same page, we are going through, basically we are seeing the first slide that is already you guys have come across or you have already seen that slide. And I believe this is the slide I will keep back and forth and throughout this semester as well as next, where the purpose or the objective of showing this slide is to make sure that you understand the design process is not a, a single chain, a series of chain or series of sequences or series of steps, but it is an iterative procedure wherein uh, in every steps there can have multiple iterations. You can basically go from step number 1 to 2 to 3 and then back to 1 and so on and so forth. So that is how the design process generally is carried out. So, and the first step that is always uh, the important step or the critical step in the design process is to identify the need. That's what we have been trying to do so far in this class till now. I mean, till this week, we have been focusing on the need identification and how to move forward with the needs for the design. So let me also quickly see. So is there an issue with finding the lectures, guys? I'm just seeing some readings on the chats which says that they are not seeing the lectures. Is it everybody is?
Yeah, I can't find it either.
I only have the first two as well.
I'm sorry.
I only have the first two uploaded to Beachboard.
Okay, just give me, let me just check. I just uploaded it. So just give, I see. Okay. It was not visible. So right now it has been made visible. So hopefully you guys can access it. Is it now?
Yep. You can see it now.
Great. Thank you. So let's go back to our slides. So is the slides back up in your screen, guys?
Yes.
Yeah, cool. So yeah, so what we are actually doing here is to get a good handle on the need identification. So before we actually discuss further about the needs, just basic vocabulary just for the record. You already know what the design objectives are. So design objectives are nothing but the feature or behavior that we wish the design should have or should exhibit. So this basically comes from answering the questions what the design needs are and why are they. So answering this question basically gives you what are the important characteristics a design should have or a specific project idea should have, and why are they important. So that's basically the answers that these questions have that will help you to understand what the design objectives are. So I believe everybody is now very much aware about this specific concept, what a design object. Similarly, if we think about, or we basically talk about design constraints and functions, you guys also are aware about that. So what the design constraints are, it is nothing but a specific limit or restriction that we apply on design objectives. And similarly, the functions basically means the things a design system or device is supposed to do. So it involves transformation of, as we have seen, material, excuse me, energy and information. So for every system that you can come across, you can basically identify its function by asking question what this specific component or object is supposed to do, or what specific function that system has. And you will always see that it basically takes some input in some form and it transforms those input into output. And that is what we actually saw during the lab sessions about how to decompose a function of a product and how to basically do functional decomposition. Some more vocabulary here. Means we already seen. These are basically the solutions, or basically the ways that we can make the methods, the way that we can implement a specific function. So for example, friction is a means of fulfilling the function. Similarly, we have seen different ways or different techniques or different methods by virtue of which a specific function gets implemented. So that is what we call as means. Now, the two things that we have not covered or we have not seen so far is what is a metric and what are specifications. So metric are basically the scale on which the design's objectives can be measured. For example, we saw that we need a high performance car. We need a car that should give me high performance. So now when I say performance, performance is a desired objective. And if I say that, how can I measure that it has got high performance? Suppose I have got 3 design engineers in my team, and I ask them to give me 3 options of a car, high performance car. Each one of them give me 3 design options. Now, if I have to compare each design against the other design, then I need some sort of a scale by virtue of which I can say one design is better than the other, or another design is superior than the rest of the options. So metric basically gives you that scale or that reference point by virtue of which you can compare one design against another. Now, if you have a specific specific data point, suppose, for example, when I say high performance car, so performance is nothing but an attribute. Now, to measure the performance, there are certain indicators, certain metrics, like it has a speed, it has got certain acceleration, it has got certain certain power to weight ratio and something else. So what are the specific parameters by virtue of which you can measure the specific objectives is what we call as metric. So high fuel efficiency car, or that means you are basically measuring in miles per gallon. So those are the metrics for specific objectives. Now, sometimes the metrics can be direct metric. Direct metric basically means that you can measure the speed, you can measure the mass, you can measure the fuel consumption. Sometimes the metrics are not so direct. You have to have some indirect metric. For example, I want to measure the durability of a specific product. For example, I want to measure the durability of a cell phone. So the desired feature for us is a durability. Now, if I have to measure this, what do you think? What can be the metric for that? Can anybody volunteer and say or suggest something that can be a metric or point or a reference point by virtue of which I can measure that a cell phone, if I have 2 design options for a cell phone, how can I measure one cell phone is more durable than the other one? How will you measure that?
You do a drop test.
You can do a drop test. That's one. And any other thing? Any other?
A water pressure test?
Yeah. So yeah, water pressure test you said, right?
Yes.
Yeah. So I mean, yeah, is there any other point? I mean, yeah, those 2 are excellent ideas that you can basically do a drop test. And when you do a drop test, you basically see by dropping the phone from a certain height, whether there are certain specific damage that is occurs inside the cell phone or not. So that way you can evaluate which of the 2 design options of a cell phone will be more durable. Similarly, you can basically do a water pressure test, or you can do a shock absorber test, or you can do many other types of testing that can not directly but indirectly gives you a measure of the desired objective of a specific product. That's what we call as indirect metric or surrogate metric. Is that making sense to you guys?
Yeah.
Yes.
Yes.
Yeah, battery life, again, somebody says, so that is also one of the ways that you can do the durability. Well, there are many other metrics that you can relate it or to the specific objective. Now, there's another term that is commonly used as technical specifications. If you have basically you have come across specifications of a specific product, let's say specification, if you ask what is spec of a mobile phone or spec of a laptop or spec of electronic consumer goods, this term is generally commonly used in those cases. Now, when I say specifications are basically the scale on which the design's functions are measured. So it is not about the objectives, but about the function. So we have to make a distinction between the objectives, which are my desired attributes, fuel efficiency, desired attribute, higher battery life or high service life, durability is a desired objective. But a function is basically the things that a system is designed or supposed to perform or to actually do or implement. So if I have to measure the specific function of a design, then the scale on which it is being measured is called as specifications. So let's say the battery should hold charge for at least 10 hours in its rated capacity. So should hold charge. So it is basically doing some action to some, basically it is doing some, it is basically holding the charge. So it is doing some, so there is some verb involved in it. So that is basically going to tell you about the system's function. And when you are measuring the system's function, those parameters are called as specifications. So these are basically the two difference between metric and specifications. And we will come across these terms when we are going to do the, once you have shortlisted your project idea and we are going to list down how we are going to evaluate different design options and how we are going to compare one design against another, then we will be using these terms more in a more like, we will see more examples for these specific terms like metric, what are design metrics, how they are used, and what are design specifications. Any questions so far?
No.
Okay. Cool. So we have seen the objectives. Now there are certain tools that are design tools that are commonly used in textbooks, basically to say that to have a formal representation of an objectives of a design, you actually do a sort of tree structure, which we call as objectives tree. So this is one specific example from the textbook where the top level requirement is that you have to design a ladder, a safe ladder. Now, when you say a safe ladder, so the first question, as we always say, that we have to ask is what the design needs are and why are they important. So the design needs are, of course, as the name suggests, needs to be safe, and I need it to be marketable because ultimately it needs to be sold to the customers, or to be sold in the market. So that are the top level objectives, which we call as global objectives. Now, similarly, and if I actually breaks down the specific global objectives and try to say how to address the needs and which are solution independent, that is, I'm not specifying any solution to that, but I'm saying that if it is a safe, how can I make it safe? It has to be stable, it has to be rigid, it has to have some stiffness. And when I say stable, stability is on basically specific floors, on level ground, or any other sort of surface. So what type of surface I'm considering. So those are the specific details that are when I'm trying to populate and putting it in a tree-like structure, that's what we call as objective tree. Now we have, but when we were doing the exercise about the finding the design objectives, we did not create any such sort of a tree structure, but what we said, we actually keep on asking questions and brainstorming together and finding out what are the list of desired attributes. So just writing those lists itself is the starting point. And then when you actually arrange them in a tree-like structure where the global objectives come first, the local objectives come later, that becomes objectives tree. Now, I'm not expect you guys to be working on a tree structure like this for your specific idea or specific project, but at least you should be aware that what these objectives tree mean. Objectives tree mean basically is that your objectives are arranged in global to local fashion. So you first arrange the global objectives and the local objectives, and that structure is basically called as tree structure. Does it make sense, guys?
Yeah.
Yes, it does.
Yes.
Good, thank you. So similarly, you have another product, and this is again a textbook example of basically designing a juice container. So if you have to design a safe juice container, what will the starting point? And you always see that whenever you go and work in a specific design process, you will never start with CAD drawings or SolidWorks design or basically a finite element analysis of product. You always start with the process and the processes to establish the need. So once you have those specific processes steps done, then you actually start working towards the CAD design, towards the analysis, optimization, and so on and so forth. So before you actually go to those steps, you need to have certain you need to follow certain requirements. I need to follow certain rules of going through that process. And for each process, there are certain systematic tools that are available to help you to go through that process. So these are just specific tools like objectives tree. So this is nothing but you are listing the attributes, listing the objectives, asking the questions, trying to find the answers, what the design needs are, why they're important, and how to address those needs. That is basically this all tool or objectives tree is all about. So I'm not going into the details about what this tree is made up of, but you can see from here itself, I'm listing off the specific bullet points that it has to be safe, it has to be environmentally benign, it should have long shelf life, it must appeal to parents, environmentally benign, it should have a reuse recyclable materials, and so on and so forth. So you can basically see it is nothing but coming up with those ideas and then arranging those ideas in a tree-like structure. And making, when I say arranging, if you see there's a pattern in arrangement. So when you say and how they are clustered together, so all the ideas or all the attributes which are related to safety are attached to this block. All the ideas that are related to manufacturing and production cost or distribution and how it is going to be handled during shipment, they are basically under this specific headline, which is low production cost. And all the other attributes that will help to make it more marketable, they are actually attached at the middle. So it is basically you are clustering similar looking ideas at one place. And that is what this tree structure is all about. Any questions so far, guys?
No, we're good.
Okay, great. So the next part is about functional decomposition. And just were doing that during our lab sessions for the last week and this week as well, that we are trying to understand the function of our design, because without understanding the functions, it will be difficult for us to come up with different solutions. And if we do not come up with different solutions or different means for each subfunction, then it will be hard to see how can we make any improvement in the design, existing design. And when I was doing this assignment or this lab exercise with you guys, I basically told you that you don't look at the solution, existing solutions to begin with. So suppose you are working with a specific project idea, you have a great project idea in your mind, you just do not jump to Google and search that what are the existing solutions for that project idea. 99.9999% chance is that already that you are thinking is already there in the market or is already there in the field. So it is very much the likelihood is that it is very close to 100% probability that whatever you are coming up with new ideas or whatever idea you are coming up with, it's already existing. So then you will basically, if you start with that approach of searching and looking at the existing solutions, then what will happen that you will get upset and you will get depressed that, okay, there is nothing to do and there is no project idea to begin with. And that is what you have to avoid. That is the thing I wanted you to avoid, and pitfalls are there. So even if the system or the idea that you are thinking exists, it does not make a difference. What you are doing is you are going through the process and trying to see what are the functions you are going to implement, what are different sub functions, what are different solutions that can happen. And you have already seen or basically gone through that process. Then you actually look at the existing solutions to make sure that there are certain improvements that you can propose, or you can basically propose some new idea on your own. So That is the whole purpose of going through this functional decomposition exercise. I hope it makes sense, guys.
Yeah.
Yeah, pretty much you're kind of just telling us to like come up with our own ideas before checking to see if they've already been done, right?
Yes. Yes.
Okay.
So I'm saying that, I mean, you were present in the lab session, right?
Yes.
And we did the functional decomposition exercise for a specific product for a vacuum cleaner. And we saw that we come up with different sub-functions, different tasks, and we come up with different means for them. So that is the step that you have to follow for every specific idea that your group actually comes up with. So for example, if your group has 4 or 5 students and you are brainstorming different ideas, I mean, if there is no specific product that already you have shortlisted or basically you have zeroed in on, then if you are brainstorming different ideas together, then the important part is you should also brainstorm the different objectives and different functional decomposition part of it. So that will give you more better direction or more better clarity on what direction your group should follow while doing the senior design project.
Okay.
Does that make sense to everybody here?
Yes.
Yes.
Any specific questions, guys? Okay, so as I said, if there are any questions, you can interrupt me at any time. So that should be okay. So for the functional decomposition, there are different tools again available to us as formal tools. Formal tools basically means what we have seen during the lab session is one specific tool, which we call as black box and glass box technique. Black box means you identify top level function and then you use your engineering judgment to list down the tasks or basically list down the sub functions, and then basically that is called as glass box technique. So that is the technique we actually followed during the lab session. There are other tools available which we call as reverse engineering or dissection. Reverse engineering does not mean that you go through the existing design and copy that. So copy that design. So that is not reverse engineering means. Reverse engineering basically means you actually go through the details of the existing design if it exists, or if the details exist, and then you try to recreate the sub function. So for example, if you have a specific product in your mind, which you or specific design solution in your mind, which you are not very sure of how to implement or what are the inputs and outputs for that, how transformation is taking place from inputs to outputs, then you can do reverse engineering of existing product and see what are the sub functions that are being implemented by a specific means. So that is the only reason that you are going to do reverse engineering, to understand the functionals of the system, not to copy the specific design components, but to understand what are the specific functions for each component is, and then you brainstorm about different means to achieve those, different means for those sub functions.
Professor, real quick, what did you say the black box and the glass box was?
So during the lab session, we talked about top level functionality, and then we break down the sub functions of that function, of that top level detail, right?
Uh-huh.
Top level functional decomposition is called as black box. I will actually show in the next few slides, we will discuss about that. And glass box means you are basically trying to see through that internal details, what are the internal components and how that transformation is taking place. So that is what we call as glass box.
Oh, okay.
In subsequent slides, we'll be discussing a bit more about that. And I was basically talking about dissection or reverse engineering. So when I say reverse engineering, the purpose of the reverse engineering is not to copy the design. It is to understand the sub functions about how the sub, or what are the components, or what specific components are doing what type of sub functions. And once you have those list of sub functions, then you actually can brainstorm to come up with different solutions for those sub components. Is that making sense, guys?
Yes.
Yeah.
Cool. So similarly, there are other tools like enumeration technique and function mean stream, which we actually saw. So let's go through the black box. Black box basically means you know the inputs, you know the outputs. What is going inside, you are not aware about it, or you are not concerned about it. So that is what we call black box technique. So for example, if you have a have to understand the functions of power drill, or you have to decompose the functional decomposition of a power drill. So I do not know what are the components or what are the systems that are there inside the power drill. But what I do know that it takes some input and it produces some output. What the inputs are, that it requires some power, it requires some force to hold the drill, and it requires some information about how much is the speed, what should be the direction of rotation of the chuck, and the drill bit. And that is the piece of information and the power or the energy that needs to be provided as an input. And the output is obviously a rotating chuck for the power drill, which is used to drill a hole or to do specific operations. Now that is what is we call as black box technique. Black box means I'm not aware about the details of the inside of power drill, but I do know what are the inputs and what are the outputs. So that is called black box technique. And then, as I said, that once you actually, if you're not aware about the details, you can basically see or basically think about how the power, electrical power gets converted into mechanical power of rotation of the chuck. Or basically that means it requires some sort of a gearbox, or if not gearbox, it requires some motor. You need to change the speed and direction. You probably need a gearbox or transmission box that can change the direction of the rotation or change the speed or torque as per the requirements. So if those are the things that if I think about the inputs, and if I think how the inputs get converted into outputs, you will basically get some idea about the details. So you are not basically here really are interested in what type of circuits are required, what specific motor is there, what type of transmission speed, whether it is a helical gearbox, whether it is a spur gearbox. You are basically not interested in those specific minute details at this point. But what you are actually doing here is that you know that those inputs that are going inside the system are interacting with each other in a manner that it gets transformed into a specific output. And that is what we call as a glass box representation.
What are the numbers referring to?
I'm sorry?
What are the numbers referring to?
What are the numbers? Numbers basically refer to a specific diagram which is not shown here, and the specific diagram has the labels of those specific components. So 9, 10 are the specific number of the diagram. So diagram is not shown here at this point of time.
Okay.
Yeah. Any other questions, guys?
This is going to be on Beachboard, right, Professor? It's kind of a lot to copy down.
I already posted this in the Beachboard. You don't need to copy down. So it's all there. You can just refer there. You can just go to a Beachboard and refer it. The only thing actually, this is, you guys have suggested to post the lectures before starting the lecture. So I'm just trying to do that, follow that part. The only thing I'm still not able to do is to edit the videos and upload it. So I'm still working on it, and it's basically as the days progress, the videos keep on piling and I'm unable to edit them and upload it. So I just don't want to upload the raw videos because there will be a lot of gaps, a lot of voice breaks and everything else. So I just want to make sure that it can be somehow edited. But if it happens that I'm not able to edit them, I'm just going to post the raw videos in the Beachboard. Okay, anything else? Any other questions, guys? Okay, so if not, this is what I was basically talking about, the reverse engineering, that when you do the reverse engineering, you already look for the existing solution, existing design details, and the best place to look at the design details is patents. So you look at the patents and see what the patents tell about the design. And then, as I said or mentioned, the goal is to understand design functions or no specific implementation. It is not to copy the design. So that is what there is a common notion for reverse engineering. So there is a common misunderstanding as well, that reverse engineering basically means you copy the design and you basically implement it. So that is not what reverse engineering means. Reverse engineering basically means you actually look at the existing solution and you improve upon it or you modify it. So that is what reverse engineering is all about. So any questions on this? The whole purpose of this specific information that I posted in this slide is to make sure that how and where you actually get to know the design details and what is critical or what is important part. The important part is, as I said, to understand the design functions and how the specific implementation takes place. So that is what the purpose of this specific slide is. So the next is enumeration technique. Again, this is another tool for doing the functional decomposition. If somehow your engineering judgment does not allow you to list all the sub-functions or your reverse engineering does not let you to see that existing design details, then what you can do is you actually go through the list of, or basically answer the questions about the function, answer the questions regarding the functions of the product by asking whether you have knowledge about the inputs and outputs, which is a very basic step. And then imagine that if the designed object ceases to exist or specific component in that specific design is not there at all, then what is going to happen? So that way it will help you to give you an idea about the specific sub-functions of a design. So here you actually list down all the activities that a specific container is supposed to do. It has to contain the liquid has to be put inside the container somehow, and somehow it has to come outside of the container. Then there has to be some mechanism for closing to resist the forces because of temperature changes or temperature extremes, or during the handling, how to resist the forces. There has to be some means to label or identify the product. So answering or getting, thinking about all these specific list of activities, you will see that you will get to know, you will get different design ideas for a simple juice container or juice holder. So it is just like you can have a paper bag or paper container, or you can have a plastic container, or you can have some simple other design solutions. So as I have seen, or we have seen during the lab session, is that the goal is to come up with different solutions by identifying the means for individual sub-functions of a product. And to do that, you have to do those decompositions. Okay, so having seen the objectives and having seen the constraints and having seen the functions, the next step that we need to do is to come up with a what is a design problem statement. So this is the second step of our design process. So if you remember, the design process has few steps. The first step was to identify the need. Second step was to basically come up with a problem statement. Third step was synthesis. So we are right now talking about the second step, which is coming up with a problem statement. And this is also one of the critical phase of the design process. So what is a problem statement? So when we are basically discussing amongst ourselves to what specific idea you would like to work on, you would see that never, as I mentioned to you, that you are going to create a Google document where you are going to list down all the ideas that you are brainstorming. You will find that all those ideas would be in a single line statement like this: to design a new beverage dispenser, or design X product X or product Y. So it is always starting with a one line statement. Whenever your ideas will come, they will come in a one line statement. And how to create a specific, a very targeted problem statement out of that one line statement is what we call as the process of identifying the need. So how to come up with a problem statement. So as I said, what you need to do is to have a good understanding of the objectives, constraints, and functions. And here I'm just giving you one example. So this is a one line statement: design a new and improved beverage dispenser for an emerging marketplace. So if I actually put in some more details, like let's say I said that our marketing team has come up with a need for this solution for an improved dispenser, beverages as a constraint, can dispense both hot and cold beverages, and should be made up of 50% recycled plastic. So these are nothing but I'm just listing some attributes, some constraints, some functions, some desired features, and I'm just creating a specific statement that is what going to be addressing the need of the customer. And that is what we call as a problem statement. So when you actually work in a field and you go in any specific company, you will see that whenever a project starts, a project always start with a problem statement. And that defines the scope of the project. So what the project scope is, what are the specific constraints, what are timeline, what is the budget, what is the requirements, deliverables at the end of the project. So those are all everything that is somehow basically somehow captured in the problem statement as well as scope of the project. So that is what we basically need to have for all the design project groups, so that before we actually start synthesizing the solutions, you are aware about the scope of the project. So you know that exactly this is the solution you are trying to implement. You are not promising A to Z solution. You're just promising a specific portion of that problem that you are solving. So no project, you will see that it solves all the existing problems in the world. So you need to basically target specific problems that your product or your project idea is going to solve or is going to address. So that is what we basically mean by coming up with a problem statement. Without a problem statement, you don't know what you are actually working on, what is the scope of your project, what is basically required to be delivered. Am I making sense, guys? Yeah.
Yes.
Any questions regarding this so far? Okay, so if not, there are some couple of announcements now. So this Wednesday, we won't have any lab session. And in the coming week, we will be having the first lab assignment that is going to be evaluated and graded. And that lab assignment will be in the form of a presentation, which will be a group presentation for 10 minutes, followed by Q&A session. And each lab session, as I said, have members, or all the group members are attending in one session. So basically it will be easy for you to present. And what you are going to present is top 3 design ideas that you would like to work on, your group would like to work on. So there may be cases where you guys are saying or thinking of taking a project from a company or some outside organization or some places. So that's fine. But for this specific assignment or this specific activity, what I need is basically you need to work on top 3 design ideas that your group thinks can be taken as a senior design project. And once you have those top 3 ideas, you are basically going to present the need and motivation for those ideas, make a list of objectives, what are the desired features and attributes and constraints, and perform functional decomposition for each one of those ideas. So that is what you are going to present for top 3 ideas on Monday and Wednesday next week.
That's it?
Yes.
Do you want us to create like a PowerPoint for it or just talk about it, or?
No, it is a formal presentation. So it will be PowerPoint slides, as I said, and the PowerPoint slides, it will be last for 10 minutes. So your group members will be presenting to the whole class. So for example, for Monday's lab session, morning lab session, all the group that are there, they will be basically listening to your presentation. Similarly, Monday afternoon, Wednesday morning, and Wednesday afternoon. And each group will be evaluated and you will be graded for your first lab assignment. Yeah.
What do you mean by identify the means for each subfunction? So like anything that we have on it, like what is it going to be used for, or?
So were you present during the lab session?
What's that?
Were you present during the lab session?
Yeah, I was.
Okay, so we identified some means for the sub functions. Where did you?
Yeah, like are you talking about the tasks?
I'm talking about the solutions for those tasks.
Oh, okay, yeah. So you list the tasks, and then we had like the specifically.
Yes.
Okay, I know what you mean.
Yes.
Perfect.
So that is what you need to do for your specific project idea. So for specific project idea, I don't know what specific project ideas you guys are working on, but let's say there is some project idea for a specific piece of machinery, let's say. So you need to identify the functions that machinery does. For example, if it is a lathe machine that you guys are working on, or is a 3D printing machine you guys would like to work on. So what the specific functions of the 3D printing machine are, what are the specific sub functions, what are the means that you think can be there for those to satisfy or to implement those sub functions. So for each specific ideas, you need to have the desired attributes and constraints, and you need to have to perform some functional decomposition. Now to work on that, I would ask you guys not to refer to any source or internet at this point of time, because as I said, you can look at the internet or any other piece of existing information after you finish the functional decomposition part. Once you finish the functional decomposition part, then you guys are ready to look at the existing solutions and see what they already exist. And this is a group activity. It is not like you can do it. It can be done by one person in a group or two persons in a group. It is a group activity. So when you are going to present it and followed by a question answer session, I will basically get to know who has basically put in how much efforts in your group to get these things done. So please make sure that each one of you are contributing, and and the group performance will tell me exactly what you are, how much efforts you as a group are putting in your project. Any questions on this, guys? Okay, so if not, then I just, the next couple of slides will basically give you some sample projects, and sample projects basically means it just give you the first bullet point. If I go back and say that you have to explain the need and motivation. So this specific slide explains the need and motivation along with the problem statement. So you don't have to worry about the problem statement at this point of time, but when you actually are presenting your specific project idea, it has to have a certain specific title. It needs to have the need, and it must have some motivating picture, which actually explains, because pictures are better than words. So instead of explaining the motivation, you actually have some motivating picture for your project idea. So suppose you are working on top 3 design ideas, so it must have some motivating picture, and it should have the need identified. I don't ask you to work on the problem statement at this point of time. We will actually work on the problem statement for the shortlisted idea that you are going to work on. Similarly, for example, it's a pill dispensing machine. So just looking at the picture, you just get an idea about, okay, what this project is going to do about, we're going to talk about. You don't need to look at the need, and you don't need to look and read the words basically. So the picture tells the whole story. So similarly, you have to find some motivating picture for your design. What is a specific picture that will convey that specific need of your project? Making sense, guys? Here?
Yes.
Yes.
Yeah. So similarly, there are other projects. Sample project slides are basically mentioned in this lecture slide, and this is just for your guidance and for reference, that what you actually need to prepare as a first slide, which explains the need and motivation of your. And as I said, you don't need to worry about the problem statement at this point of time, because we will come across the problem statement after we shortlist a specific idea. So just motivation and the need, a motivating picture and title and the group member. That's the first slide for your one project idea that you need to prepare. Any questions so far, guys?
So just to reiterate what you said, Professor, for our presentations come the following week, we don't need to include a problem statement, just a motivation or need.
Yes, exactly. Yeah. But and this is just one slide. So if I go back, I am asking you to also present the list of objectives and functional decomposition. So the slides I'm presenting or basically giving you a reference is only for this bullet point, which is to establish. You still need to add the slides about the objectives. You need to add the slide about the function and the means that you have identified.
Okay, awesome. And then we're also outlining all three of our ideas, right? Just not one.
Yes,
Right?
yes, yes.
Okay.
Okay, any questions, guys, so far?
Professor, I have a question.
Go ahead.
So out of the 3 project ideas, you're going to choose which one we work on?
I'm not going to choose anything. I'm going to help you to choose the one that you're going to work on.
Okay, thank you.
So the choice will be yours. So that is not, I'm not going to say anything about do this one or do that. So it is all based on your group, not only you, but your group as a whole thinks about a specific idea or what specific project idea you would like to work. That's what we are going to do. Okay. Any other questions, guys? So as I said, the slides are already there in the beach board. So before we actually move to other topic, another concept about the stresses, I would basically stop for a couple of minutes just to take a few minute break. And then we'll start a specific concept about mode circle, as I was mentioning at the beginning of. So we will actually go through that concept. So what are stresses and strains and some basics about the analysis of the machine components and how. So let me know if there are any questions or not, guys, before we actually take. Okay, guys, so we can resume our discussions and basically wrap it up. So just have 2 slides and basically they are related to the analysis portion of it. So is everybody able to hear me properly?
Yeah, we can hear you.
Yes.
So when we talk about the analysis, and that's what we are going to do from now onwards, and we are going to follow the textbook portion of this course, which we basically Shigle's textbook. The most basic concept that we are going to learn or we have to learn is about the stress in a specific material. So before we actually go into detail about the stress, can somebody tell me why this is important, why the concept of stress is important in a material, or to understand the concept of stress in a material is important as a designer or as an analyst, stress analyst, or even as a designer, why it is important?
Just basically just so you can understand the limits or the potential of whatever it is that you're making.
So limits of what? Can you be a bit more elaborate on limits on what?
Of like your material. So like how strong it is,
Mm-hmm.
or how much abuse it can take. So like if you're designing let's say like a lawn chair, obviously you don't want it to break on a person. So you have to design it with the proper materials to withstand a certain weight capacity.
Yeah. So as you basically continue on your line of thought. So the reason that we are concerned about the stress is to make sure we can avoid failures in a material or in a design. So as a design engineer, the number one responsibility we have is to make sure that the product or that specific component you are making does not fail in service or when it is basically getting used in the field. So to prevent the failure, you need to understand what kind of stresses or strains that exist because of the loads. So any mechanical component you can think of, whether it is a gear, whether it is a pulley, whether it is a shaft, whether it is a transmission axle, whether it is suspension, whether it is chassis frame, whether it is a simple space structure, any component that you can think of is basically there to serve our purpose of withstanding forces and movements that are going to be applied from the external agencies. And the specific component that is being designed has to be designed such that it should be able to withstand failure, or it should be able to withstand all the loads without any failure. And to prevent that failure, you need to understand what type of stresses are coming in the body, what type of strains are coming inside it, and what are the limits of the material that can withstand those type of stresses and strains. And that is the reason that we are basically trying to have a very good understanding about the concept of stresses and strains. And then we will basically move towards how the failure happens in a material and what can we do to prevent the failure. So again, before we actually move any further about the concept of stresses, is there any specific solution that you guys know from the top of your head that will help you to prevent failure in a material? Can you guys just think from the top any points that you come to your mind to prevent failure in a material?
You add more material to it.
You add more material to it, that's one. You can make it more material, but what are the cons with that? The cons will be, it will be more weight. The weight will basically pile up. So you add the material, but then the concern will be the weight will be higher, and then that means you will have more cost. And that will basically means that there are other consequences again about that. But let's say you have weight and cost as a penalty for making it safer. Anything else that can come to your mind, guys?
Use a stronger material.
Use a stronger material is another solution, but the cons is that it will be more costly. It will be difficult to manufacture and difficult to process. The manufacturing processes that are required to shape it or to basically work with, it will be very difficult. The stronger the material is, if you work on a machine shop, you basically know that the stronger the material is, the more difficult it is to work with it. Whether it is welding characteristic, whether it is just like machining, it is hard to work on. So you require more manufacturing time, more manufacturing cost, and even the raw material cost will be even higher. So the cost and manufacturing processes will not basically be supportive of using stronger materials. Anything else that you can think of, guys?
You can also heat treat it.
You can heat treat it, but heat treatment only does very specific functionality. It does just hardening of the surface. So heat treatment only helps you to harden the surface and prevent the wear and tear on that. So apart from that, heat treatment. So when you say heat treatment, it is surface heat treatment, or what you're talking? Are you talking about the heat treatment of the whole part, or are you talking about the surface heat treatment?
Of the specific part.
Okay, so that is true. You can do the heat treatment and you can improve, you can relieve some of the stresses or residual stresses. But then the cons for that is that, again, the heat treatment is adding cost to that process altogether. And second thing is that because of the heat treatment, there are residual stresses that come in the system. So you are not only relieving the stresses, but somehow if your component is an assembly, it is not just one piece, but an assembly, then assembly of the whole components is very difficult to heat treat, and then the residual stresses will come in the system. So that is basically the cons for that. Does it make sense?
Yeah.
So yeah, so heat treatment is a solution, but it works only when you have individual components to work with, not the assembly. You cannot just do the heat treatment for the entire assembly. So, and here,
what are you like asking us for, Professor? Like a solution to make a product stronger without any downsides, or what?
no, I'm just saying that you just throw me the ideas and I will tell you the cons.
Okay.
So I'm just asking you, okay, as a designer on top of your head, just forget about any specific product or any specific component. Just on the top of your head from your experience, if somebody asks you, how will you make the product stronger, or how will you make it foolproof, that show that it does not fail in service? So what are some typical points that come to your mind? So as you said, you can add more material to it. You can use stronger material, you can heat treat it. All these are excellent points. They help to prevent the failure. But for all of these points, there are certain downsides to it. So I'm just asking you to do some more thinking about how can you prevent failure. What can be other ideas you can throw at me?
A good.
Composite material.
Sorry, come again.
Composite material.
Composite materials. So if you talk about composite materials, they are very excellent choice candidate materials all across disciplines, in several disciplines, whether it is aerospace, whether it is automotive industry, they are using composite materials. If somebody doesn't know about composite, they are basically materials which are stronger, which are lightweight, have high stiffness. The downside of these composite materials are that people still in the research area are not sure about what are the different modes of failure for those composites are. So there is a wide body of research and literature that exists for conventional materials like aluminum, steel, different grades of steel. There is a lot of catalog you can find and you can look at the basic properties, but you cannot find those catalog for composite materials. For composite materials, every time you change a laminate sequence, if somebody knows about what laminate sequence laminates are, so you basically have different plies that are stacked together and you cure it in a vacuum bag using vacuum bag in an oven and you make a composite. So when you have different plies stacked together, they have different modes of failure. So if you change the design, if you change the plies stack up sequence, the failure will be very different. Modes are different, will be very different. So there's so much uncertainty still exists in composite that is not very easily widely used. So that are basically the cons of it. Are you getting what I'm trying to say here? No.
Yeah, that makes sense.
So the purpose of me is not to make you say that, okay, we cannot prevent the failure. The purpose of me is to make sure that there are so many uncertainties, so many points that exist that will prevent you as a design engineer to take steps to not implement a specific solution. And the whole purpose and whole objective for us to learn in this course is hopefully that you know the different ways, different methods, and different solutions. And you basically do trade-off study for each one of them. So you just do not stick to one solution. So suppose you are guys, one of you said stronger material. So that specific person should not be constrained in only thinking about stronger material. That person should also think about heat treatment. That person should also think about composite. That person should also think about stronger materials. So you don't need to just think about one specific solution, because one specific solution will not be useful in a specific application. You have to think of multiple solutions together, and you need to have a trade-off study for each of these different solutions that will help you to come up with an optimal solution in the design field. That's the whole purpose of this discussion. Does that make sense, guys?
Yes.
Yeah, that makes sense.
Professor, one thing that I know, pretty much any manufacturing, don't they always, you're always supposed to overbuild something so that it's better than what the max capacity is supposed to be. Does that make sense?
So that's an
It's
excellent point.
It's
And
over engineering.
no, it's not over engineering. What we actually call that is a factor of safety. So I was basically looking for that answer as well. And I was somebody was hoping that somebody would throw that idea to me. And I was basically ready for that, the specific points that I want to discourage you to use that. So that thing that you're talking about is to over design is basically called as factor of safety in engineering. So when you say that you in any manufacturing or in any design form you go, there is a specific factor of safety that you have to use in your design. And I believe you guys have probably come across this term a lot in your previous studies, whether it is 373 deformables or somewhere else. Am I correct, guys?
Yes.
Yeah.
Yeah. So can somebody tell me what factor of safety basically means? Of course, everybody know we multiply that factor of safety with a specific material property and make it over design. But physically speaking, intuitively, what is a factor of safety?
As if you should be able to take twice the load, that means the factor of safety is 2.
Yeah, I mean, yeah, that's technical term. That's perfectly correct. I mean, that's perfect answer. But still, sorry, I'm hearing the echo of my voice. So can you please lower your your laptop. So when I say factor of safety, the intuitive meaning of factor of safety is basically, it is a measure of, or it is basically a measure of how do I say, of our ignorance. So factor of safety is nothing but, I mean, we can say all, play with all the nice words, say we can make it twice, we can increase the life of it by twice by increasing the factor, using the factor of safety of 2. But eventually this number is nothing but it measures how much ignorant we are about the design process and situation. So as a design engineer, if you see that no design engineer in this world actually uses a factor of safety equals to 1, you will never find somebody says that factor of safety is 1. I mean, I have never come across that. And it is basically saying that nobody is 100% sure the design is going to work. So that is why people say that, okay, I will use design of factor of safety 1.5, 2. The more the factor of safety is, that means the more inconfident you are about your design. So the more confident you are about your design, the factor of safety is going to be more and more to bringing towards 1. It will never be 1 because you will never be 100% sure whether it is going to work or not. But the lower the factor of safety is, that means the more confident you are about the design is going to work. The higher the factor of safety is, that means you are not confident about what type of loads are coming in the system, what type of failure is going to take place, and so on and so forth. That is what we talk about factor of safety. Does it make sense, guys?
Yes.
Yes.
It's basically nothing but is a measure of our ignorance. That is what we call as factor of safety.
And as your factor of safety increases, doesn't your price usually increase, or your cost?
And the reason we all know that, because your factor of safety increases the weight of the material. So when you somebody says it's over design, it is basically that what you are using the factor of safety, higher the factor of safety is, that means you're putting in more material to it. And when you're adding more material to it, that means you're adding more cost to it, and everything else goes high. Okay. Can somebody know what is the factor of safety people use in aerospace industry?
I believe I looked it up the other day. It was 1.5 to 2.
Actually, 2 is very high. Generally, it's 1.25 to 1.5. So they work in very close margins in aerospace structures, because the aerospace structures have to be very thin structures, whether it is space structures or whether it is even commercial plane structures. So those structures have very good confidence in the design. So you can see that 1.25 is a very small number. It's as close to 1 as possible. So the aerospace structures generally are have very small factor of safeties. For other for other applications, whether it is commercial application or there is a machinery or some other components, you will typically find a factor of safety close to 2. But generally for aerospace structures, the factor of safety is around 1.25 or a max up to 1.5.
You said 1.5?
Max, yeah.
Oh, okay. That's probably to save weight and probably cost, I guess.
Say weight. Weight is the most important concern for aerospace structures. How can you have a higher strength for a low weight design? That's always the concern. Okay, so any other thing you guys would like, have any point you would like to share or have discussed? So I was basically trying to wrap up our discussion of the concept of stresses. And stresses, when I say, if I just directly tell you what stresses are, you probably by now you probably know what stresses basically mean. So if I ask you stress, what will be your, the go-to answer would be? Force per unit area, isn't it? Yeah, guys?
Yeah.
Yeah.
Yes.
So that is actually not going to be the case in this course. You're not going to use that specific definition, because that definition only works if you have a uniaxial load and you are having uniaxial stresses. Then yes, stress is force per unit area. But if I say, is the definition works for bending cases? In the case of bending load, bending, you know, right? When you apply a specific bending moment, the component bends. So in that case, will the stress still be force per unit area? Okay, but let me actually switch to document camera here. So what you are basically telling me is the concept of stresses for a uniaxial load case, which means that you're applying a load in one direction and you take a cross section, and you, in this cross section, if you want to find the stresses, you can say that whatever the area is, so let's say the cross section is a square and it has got an area A, then the stress in that cross section is basically given by load divided by area. That's what your stress is, isn't it?
Yes.
Yeah. Now, if I say that you have this simply supported beam, and you apply a load P, will the stresses be the same like this, force per unit area?
No, then you'll need to take the moment.
Yeah, so basically where the stresses would be maximum, do you think?
In the middle?
In the middle. And the reason that it will be maximum in the middle, because if you do the bending moment diagram, the bending moment diagram shows you that the bending moment is maximum at the middle. And this is basically going to be P times L over 4. So this is M max. And why is it MP times L over 4? Because the reaction is P over 2 each side. And the maximum bending moment is, if this is your length, total length is L, then P over 2 divided by L over 2 is PL over 4. That will be your maximum bending moment at this point. And the stress is due to bending, if you remember from your courses earlier, it is given by mz over I, where mz is basically for this cross-section area z, this is x, okay, let's say this is y, so this is y, and this will be z. So sigma bending will be m times y divided by I. So y is the axis which is on the cross section plane. So is everybody following it what I'm doing here right now?
Yeah.
Yeah, so sigma bending max will be PL over 4 times, if this is height h, then it will be h over 2 divided by moment of inertia. That will be a bending moment. Now, if you say now that bending stresses is force per unit area, I do not see here force per unit area. So this is completely different stress here, right, guys?
Yes.
Is everybody following it so far?
Yeah.
Yes.
Yeah.
Okay, so I will not, excuse me, go further into the discussion about Mohr circle. We can take it in the next class. But what I will actually try to finish this class or lecture with a specific representation of stress for this bending case and for this uniaxial case. For uniaxial case, you know that when I apply a load in a uniaxial direction, then the stresses are all acting along the direction of the load. So which is along the direction of the load, it is given by P over A. So if this is your axis as x axis, this is let's say y axis, then I know sigma x is P divided by area. Is everybody with me so far?
Yes.
Yeah.
Yep.
And when I talk about bending, what happens that during the bending, the load will basically cause a deformation like this, right? Because of the bending that is taking place. it is exaggerated, but the load is going to deform the beam like this. Is everybody with me?
Can you move your camera down, please?
Yeah.
Thank you.
So is everybody with me on this?
Yeah.
So which one is the tension, which one is compression in compression?
The bottom
top
half
surface.
is in.
Top surface is in compression. Everybody agrees?
Yes.
And the bottom
Yeah. Yeah.
tension, right? Okay, so now my question is, or think about it. So whether, how will I represent the coordinates or the stress for sigma bending? So sigma bending basically means due to bending, the stresses will be negative on the top surface, positive on the bottom surface. So what would be the subscripts for this sigma? So for this uniaxial case, since the stresses are all in the acting in the x direction, I represent it by sigma x. So what should I say here? Is it sigma? But this cross section is given by this, which is, again, I'm drawing it here. The cross section of this beam is given by this. So whether it will be sigma x, sigma y, or sigma z, what do you guys say? What is sigma bending will be? Is it in the x direction? Is it in the y direction? When I'm just apply a load, is it applying in the y direction or is it in the z direction?
That's in the Y, no? Oh wait, no, sorry. In the
Oh, sorry. Here it is y and this.
yeah.
Yeah. So, okay. So which direction do you think the stresses are going to come? In the z or in the x?
In the X.
So I just, I'm asking you guys to just think about the stresses that are happening in this system and in which direction it is happening. Is it happening in X direction, in the Y direction, or in the Z direction?
It's in the X direction.
It's in the X direction. So how many of you think it's in the X direction? It's a difficult question to get because I will not know how many of you think about it. But is there somebody who thinks it will be in the Y direction?
You're talking about stresses?
Yeah.
And this is for shear.
No, I think they're in the X.
Okay. So you guys have great insight, I will say, because most of you would have answered in the class about the Y. But here I am getting the response as X, and that is good because that means you understand what the stresses are in what direction. So when you are talking about the stresses, what you can see is, or you can do is, always think of making a small discrete element like this. So assuming that it has made up of different layers. So if I have a small layer of material on the top, if I see the small layer of material is getting compressed and in what direction it is getting compressed, it is getting compressed in the X direction. So that is why the bending stresses that are going to come is basically will be in the X direction. Similarly, if I look at the bottom piece and think that this is a small piece that is attached to the beam, then this piece is getting extended. And what is the direction of the extension? Extension of direction is in the X direction. So again, that means the bending stresses that are happening in the system are basically along the X direction. So this sigma bending is nothing but is acting on the X direction. And I have not made the correct representation for Z because Z would be actually opposite direction because X and Y will cause a Z in the outside the plane. So that means this is a negative Z direction. This is not a positive Z direction. Is everybody with me so far?
Yeah.
Yeah. Yeah.
Yeah. So the reason I'm insisting you guys to have understanding about this X component here, because the stresses we will see, and we will actually cover this topic more in detail in the next lecture, that stresses at any point in a body is represented by representation of stresses along a cuboid, a cube, a three-dimensional cube in Cartesian coordinates, where each face has got a specific component. Each face of this cube, it has got 6 faces. Now each face has got one normal component and 2 shear components, shear stress components. So this is tau x, y, and this is tau x, z, where the first subscript here represents the direction of the normal. And the second subscript represents the direction along which the stress is pointing to. So when I say tau xy, tau, the first subscript represents the direction of the normal. So this face has got a normal in the x direction. So it is tau x. Why? Because it is basically acting along the y direction. This stress component, again, it is acting on a face that has got x as a normal, and it is acting along the direction where it is z, along the z direction. So that is why it is called as tau xz. Does that make sense, guys?
Yes, it does.
Yeah.
Yeah. Yep. So we will actually, again, try to understand these specific components of stresses on each 6 faces of this cube, and see why this representation, why the reason I'm insisting on this specific x and y and z subscripts will basically make sense, and will be related to what specific calculations. So we will actually come back and discuss this in our next lecture.